Hello and welcome. So today we are going to look at the Weiss variance trade-off. So first of all, I am going to make some assumptions. That let's look at the assumptions that I'm going to make. That let's suppose that the examples or the training data you have is getting generated from, or you are taking it, or you are sampling it from some distribution D, right? And from the same distribution you are taking the training examples, and from the same distribution you are taking the test data also, right? So on this training example, you are going to train your model, and after training you are going to test your model, right? And those two data are getting generated from the same distribution, right? That we are calling it D. And all these sampled sampled examples that we are generating are independent of each other. So let's suppose that we generated m examples from the distribution D for the first time, and maybe in the next time we generate again m examples from the same distribution. So what I'm saying that these two sampled examples will be independent, right? So there would be no relation on generating m samples from some distribution at two different times. So these two samples are going to be independent, right? So this is the second assumption that we are making. Okay. So far what you have seen, that you will have some data, right? You will have some training examples. So let's suppose that you have this m training example, and all of these m training examples are coming up from this distribution D, right? So from this distribution D, you are sampling, and you have this m training examples, right? And once you have training example, what you do is you feed or this training example to your learning algorithm. So let's call it LA, so learning algorithm, and you train your model and you get your hypothesis function, right? So this theta is nothing but the property of hypothesis, you can say property, or you can say the parameter of this hypothesis. So you have seen this, right? And we have already, like, this is the basic, right? Like how we trained our model. So we will have some examples, train example, and we feed this example to some learning algorithm, and the output we learn is a hypothesis, and right, hypothesis, or you can say that we get some optimal value of the parameter that we are saying is the theta, right? So you see that these samples that we are generating from some distribution D will be some random variable, right? And this learning algorithm is some kind of function that will be a deterministic function. And if you give the input to this deterministic function, a random variable, what you are going to get in the output is a random variable, right? So if you give a input to a deterministic function as a random variable, then output you are going to get is a random variable, right? So the point is that this hypothesis function is again will be a random variable. And what we can say about that so if it is a random variable, then we can comment on this that it will have some distribution as well, right? Because if so, that is what, right? So this is the one, this is the first time that we have sampled m example, right? Maybe next time we will sample again some m examples from the same distribution, right? And we will fit this to learning algorithm, and next time we will get some hypothesis function that we can call is h1 hat, or maybe h2 hat, here h1 hat or h2 hat, right? So this process we do, right? Because right, and once we have this hypothesis function, now once we have our predictor, then we can feed input to it, right? And we can get the prediction of your house, right? We can get the output, right? So this h hat is a learned hypothesis, right? This h hat has learned from some sampled example, right? This is what, so this is our estimation. This is not we can say the actual thing. Why? Because next time you will sample, then this sample may get differ from what you have sampled previously, right? So next time what you will get a estimated hypothesis function that would be a little bit different from this previous hypothesis, right? Okay. So there would exist some ideal hypothesis, right? And we don't know about that ideal hypothesis, right? That we call that hypothesis as a true hypothesis, right? So let's define this h star or theta star as a true hypothesis, and this is unknown to us, right? Unknown to us. Why? Because we don't know that what is the true hypothesis. If we would have known that what is the true hypothesis, then why would we need to make the estimation of hypothesis, right? But we can assume that this is a true hypothesis that we want to achieve, right? So the main point is here that all the models are wrong, right? The practical question is how wrong do they have to be not be useful, right? So we can say that all the models are wrong, but the practical question is how wrong do they have to be not be useful, right? So that is what I told you, that we will have this estimated hypothesis function, and this is some ideal hypothesis function, or you can say the true hypothesis function that we want to achieve this, right? Okay, so that was the assumption that we have made, and now let's proceed. So let me remind you that you have already seen this that Weiss variance thing in terms of the data view. Let me remind you that let's suppose that you train your model with a straight line, or maybe some with higher degree polynomial, and maybe with even more higher degree polynomials, right? So you have already seen this, right? So this is overfitting, right? This is underfit, right? And this is just right. And you see that this overfitting is, we can call it the high variance, and this underfit is a low, sorry, a high bias, right? And this just right is somewhere between high bias and this high bias and this high variance, right? And we can look. So let me see that. Okay, so this you have already seen, right? That in terms of data view, this overfitting is the high variance. So the point is that this model is not good for unseen data, right? Because it is fitting completely to the given training example, right? If some unknown data came to this model, then this model is not going to fit, right? And the variance that with the different example, or with the different data, or with different scenario, this model will have a lot of variance, right? So this will have the more, you can say, error with unknown examples, right? So that is why this overfitting leads to the high variance, right? And this underfit example, that so here what is happening is, now let's look at this parametric view, right? So we have this parameter theta1, theta2, and I'm just taking the two-dimensional case. You can thought of this in n-dimensional case, right? So we have this theta1 and theta2, and this star is representing the true hypothesis, a true property of the hypothesis. So what is true? So this is what we have explained, that true hypothesis that exists somewhere, but this is not achievable, right? And but we tend to achieve this, right? So this is, the star is a true parameter, right? And we go through this process. So what we do, we first time we sample some m examples from this distribution D, and after sampling we go through this learn algorithm, this learning algorithm, and we learn a hypothesis. Let's call this hypothesis as h1 hat, right? And let's represent this as a dot. Now next time what we do, we again generate m examples from this distribution D, and again we feed this m data to this learning algorithm, and we learn a hypothesis, and let's call this hypothesis function, that is h2, and that will have associated parameter, that let's call it theta hat 2, and let's call it theta hat 1. And again what we do, we repeat the same thing. So we are going to get some class of hypothesis, right? So if we do perform this n times, then we are going to get the n number of hypotheses with the given data set whenever we are generating, right? So so let's suppose we first time we sample the data, we feed into the learning algorithm, and we get some hypothesis that is somewhere maybe a little far from this true value, true parameter, right? And again what we did again, we sampled m examples, again we fit to the learning algorithm, and we get some hypothesis function that is, let's call that hypothesis that is maybe very near to this true value, right? And again we did the same thing, and we are going to get some hypothesis. Again we are going to get some hypothesis somewhere here. So we are going to run this lot of number of times. We are going to generate, and we are going to learn our hypothesis. So maybe we will get a lot of hypothesis, right? So these individual dot represents the hypothesis, or you can say the parameter of the hypothesis, right? And maybe we will get some this kind of, right? Or maybe this, all this dot represents the hypothesis, right? And maybe this, right? So you see that all these hypotheses, right? All these hypotheses are far from this true value, right? So this is what you can say is the high biased, right? Again all these hypotheses are far from the true value, so this is again the high bias, right? And all these hypotheses here are somewhere around the close to your true hypothesis, that then in this case it's a low bias. And you see that in this case also we have the hypotheses that are somewhere around to our true value, right? So in this case also it will be low bias, right? So and you see that each hypothesis are very close to each other, you can say in this case, right? So we can say it will have some low variance, right? Because all these hypotheses are, for each sample all these hypotheses are varying very little, right? So it will have low variance, right? And again in this case it will have the low variance, because all the hypotheses are very close to each other. So with the, and all these hypotheses have generated from different set of sample data, right? So this will have the low variance, right? And here you see that so let me explain you one more thing, that let's okay. So this here again we will have some, all these hypotheses are very close to each other, then it will be low variance, right? And here in this case that you see that these hypotheses are spread away, right? So this will have the high variance, right? And okay, let me do one thing, because these two I have made the same. So let's take this like this. So maybe this is far from the true value, all these hypotheses, but these are a little bit spread, right? So we can say that it will have the high variance, right? So So if you look at this picture, then this will represent your, from bottom to top, it is bias is increasing, right? It's a low bias and high variance, and from uh, here to here, it's a variance, right? So basically, what question you will ask yourself, that is the sample distribution around the true parameter? If answer is no, then it's a high bias. Let me read one more time. Ask yourself, after doing this example, right, you will have to ask yourself that is the sample distribution around the true parameter. What does it mean by here sample distribution? So here I have mentioned that these hypotheses will have some kind of sample distribution, right? Some kind of distribution as well, right? So or you can say is all the hypotheses that have been generated from the different sample are around the true parameter. If you got the answer no, then it's a high bias. And how you are going to recognize the variance is the how dispersed the sampling distribution, or how dispersed your hypotheses are from different sample. If it is too dispersed, that means it will have the high variance. If it is not too much dispersed, then it will have the low variance, right? So this is how you can look at and you can decide that which will have the high variance and which will have the low variance, right? So that is what we see from the parametric point of view, right? Okay, now let me talk about this training error, right? So basically you have seen this data view, right? So here we have some simple hypothesis, right? Simple learned hypothesis. And here we have some complex learned hypothesis, that our hypothesis have learned some complex expression, right? So basically in when we have this simple hypothesis, then we will have, so this hypothesis we have got by from this on this training error, on this training example, right? So if we want to minimize this error, I mean to say that so this hypothesis we have learned from our training example, right? And if we want to minimize that, then obviously what we are going to do, that we are going to touch each and every example, right? We are going to satisfy each and every example. And that case we will have some more complex hypothesis, right? The learned hypothesis will be more complex. Here we will have some hypothesis, but that will not too complex, but in this case it will have some complex hypothesis. But here if you see that for each example that curve is passing through it, right? So we will have the training error 0, right? Because we have made, or we have trained our model on the training error, right? And what we are doing is we are testing on the training error itself. So obviously if we have satisfied each and every point, then training error is going to be 0, right? So the main point is that to reduce the training error, if you increase the model complexity, then you can reduce the training error. So if I have to drop this model complexity for this training error, then here you will have some simple kind of model, maybe a straight line like this, and here you will have some more complex model, right? But here you will have this very less training error, but with the simple model you will have the more training error, right? So this is what the training error is. Now the question is training error a good measure of predictive performance, right? So for the prediction, is the training error a good choice or a good measure? Can we say no, right? Because this hypothesis that we have trained or that we have modeled is based on the given example, or based on the given training examples, right? It haven't seen the new examples, right? Then it would be not good to say that if we reduce this error, then it is going to be 0 for all the unseen example. Also we can say that this training error is not a good measure, right, for the predictive performance, right? So what we need here, right, we need a true error that we call the generalization error. Okay, now let me define what is this generalization error or the true error. The true goal is to minimize error on unseen futures example, right? If you have made some predictive model, then it should give us maybe a minimum error with the unseen examples, right? Not the minimum error, but we can say it should have that tolerable error, right? Where we should get convinced that yes, this could be the answer, or this could be the predictive value for this given example, right? So the point is that our true goal is to minimize error on unseen future example, right? So if we talk about this training error for this predictive performance, this training error is not much useful, right? So what we want is to minimize the error which example haven't seen yet, right? So how well we do on future data, that is the question, right? And also we don't know about the future data, but that data will be, right? We trained our model, but we still do not have the idea that what kind of data is coming into our model, right? What will be the future data that we should have, right? And even we don't know what labels yi it will be, right? And but what we know is the range of all possible xi, yi, right? So let me give you an example. Suppose you want to predict the handwritten digit, right? Maybe something like 1 or 2, right? So you know to predict the digit that labels would be from the 0 to 9, right? This is known, right? What we know is the range. The y label, we know that the digit will be from 1 to 9, and also x, that if that frame is of 20 by 20 pixels, then we know that with the black and white pixel we will have this kind of pixel, right? We know the intensity of pixels, right? So these two ranges we know, but what is going to come up or what feature example is going to come up for our model, that is unknown to us, right? Okay, so in this case, what we do is we define a true error, right? A true error that we call that, let's call it that EG, or the generalization error, as this. So it's the error. It's the error between the hypothesis, the true hypothesis of let me see, and what is the label, right? And this is how we define this error, right? So this is the error, and this is in between hd of x. So this is the, this you can say is the like you can say this as a true hypothesis, right, that we have defined earlier, right? And this is the label, right, y. So the difference between these two will give the error, or whatever the function you use to calculate the error. So I'm writing it in general that error will be from these two, and this is the probability distribution, that how often we expect to see any x and y, right? So this is the true error, right? And it is not possible to calculate this generalization error, or the true error. Why? Because we have no info about this xi and yi, right? So what we do is from the training example itself, we separate few data and we treat as an unseen example. So maybe we will have some training, maybe we will have some m training example, and what we will do that we will split this n and m minus n. So we will train our model on this n example, and we will test our model on this m minus n example. So since we are training our model on this n example, so this m minus n example will be unseen to our model, right? This will be unseen to our model. So this is what we can do, right? So extending this idea, now we can define a expected test error, right? So the expected test error is going to be on this m minus n unseen, that haven't seen by our model, right? So we define this error. So again, we are going to take the error and we are going to get the average of this error that we are calling it the expected test error, right? So again, let me draw. If we increase the model complexity, how is the training error is going to look like? What you can say. So we have seen this earlier, right? This is what. So if we increase the model complexity, then it is going to reduce. And if I ask you that that how the test error is going to look like, right? If I ask you that the test error is going to, how the test error is going to look like, right? So the test error would be like this. So so for the simple model that so here we this is so in the type the model complexity is increasing, right? So on the test error we are somewhere here. So this and it is going to increase again, right? So this is the test error, and this is the training error. Okay, so okay, so what's happening here, that in this region we will have, in this region we will have some model that will have the simple model, right? So if we have simple model, then and if we test our model on this simple model, then this even with the unseen data, we will have some error that will be more, right? And in this direction we are increasing our model complexity, right? So this is somewhere in between. You can say that here we will have the minimum test error, and after that, due to the overfitting, what is going to happen, that we will again we will have some test error that will increase, right? So this area is good for us, right? And these two area will, due to underfit, we will have test error greater, and here we will, due to overfit, we will have the test error greater, right? And this area that we are interested in, right? So this was the test error and the training error, right? So we saw about the training error and we saw about the generalization or true error, right? So let me give you one more perspective, that how we can see this generalization error, right? So let's consider this some space of hypothesis. So we have given this space of hypothesis, right? And let's assume that this is a class of hypothesis, and we are calling this class of hypothesis as H. And what does it mean by class of hypothesis? So maybe you will train your model with the SVM, right? So in SVM, with the different value of lambda, so you will have a lot of trained SVM, right? So, and again you will have the model with the logistic, maybe, and maybe with the linear regression. So it's a class of hypothesis. So maybe you will have SVM class, or maybe you will have where if we are talking about SVM, then we will have a lot of hyperplanes, optimal hyperplanes, with maybe some twist with the regularization, or right, and with again it may have some linear regression class. So you will have some lambda value, and so it's a class of hypothesis, right? And in this class of hypothesis, this G is the best hypothesis in the class, right? So, and this H1 and H2, these are the different hypotheses of your class, right? And out of this different hypothesis, G is your best hypothesis learned, right? And this H star is your again a true hypothesis, or you can say the ideal hypothesis, right? So this is again not achievable, but we tend to achieve this, right? So that is what H is the class of hypothesis. H hat is the hypothesis learned from the finite data, and G is best hypothesis in the class, and H star is the best possible hypothesis, right? Now again, let me define a few more terms. So this epsilon H star, what we call is the bias error or irreducible error. Why we are calling it this epsilon H star is the bias error? Because you see, this is our ideal hypothesis, right? True hypothesis. And if it have some error, then already we are considering it as a true hypothesis, then obviously that error is not going to reduce further, right? Right, and so 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 maybe this irreducible error are coming from the data generation itself, right? So maybe that you are sampling your data for some value of x, you are getting some y, and again for the same value of x you are getting some y too, right? So this error is from the data generating process, right? And and we cannot reduce this error, and that is what we are capturing this error in your best hypothesis possible, that if it has error, then that error is going to come up from the data generating process, and that is irreducible error, right? And now we define one more term, that is approximation error. And how we define it: the difference between your true hypothesis and the best hypothesis in your class. So this difference is your approximation error, right? So epsilon g minus epsilon h star, the difference is the approximation error. And let me define one more thing, that is the estimation error. And how we define is the difference between your hypothesis that is in your class and the best possible hypothesis in the class, right? So that we are calling it the estimation error, right? So difference between the hypothesis that is in the class and the difference between the error in the hypothesis in the class and the best possible hypothesis, that we are calling it the estimation error, right? And if you add these two, right, then on the right hand side we will be getting approximation error plus estimation error. So estimation error plus approximation error, and these two terms are going to cancel out, right? And this term will go into right hand side, and this is what we are calling it as a irreducible error. So here is the irreducible error, right? Okay, now let me further talk about this few points on this approximation error and on this estimation error, right? So what we have written here, that how far the entire hypothesis class is from the target predictor h star, right? So this approximation error is how far the entire hypothesis from the target predictor, right? From the target predictor. If we increase, if we have larger hypothesis class, so maybe let's call this like this. If we have larger hypothesis class, then what we can call that this approximation error will get reduced, right? And let's talk about this estimation error. So this is how good the predictor h hat, so h hat is again in the class, returned by our learning algorithm, is with respect to best hypothesis class. So this is the best hypothesis class, right? And somewhere we have this h hat in the class, so we are comparing it with the best hypothesis in the class, right? So and all these h are learned from the given data set, right? So that is what we are calling that how the predictor h hat returned by our learning algorithm is with respect to best hypothesis class. So we are comparing with the best hypothesis class in the class with whatever our hypothesis is learning from the training data set, right? So if larger hypothesis class, so if we make the hypothesis class larger, then estimation error is going to be higher, right? Why it is going to be higher? Because it is hard to find good predictor with limited data, right? So that case we will have the larger estimation error, right? So you see there is a trade-off between this approximation error and between this estimation error. If you increase the class hypothesis class, then this approximation error is going to reduce, right? But at the same time this estimation error is going to increase, right? So at the end, if what we have done, we have added this, right? So this is what we are capturing is a true error, right? True error. So we were talking about this here about the true error, right? That generalization error and the true error, that is what we have captured here, right? The true error is the sum of estimation error and the approximation error and this irreducible error, right? And this irreducible error we cannot further reduce it, because it is inherently came from this due to this data generation, right? And there is some way that we can play between this approximation error and this the estimation error, right? So there is some trade-off between these two errors that we can twist, and we can have some balance between this approximation error and this estimation error. I hope it is making a little bit of sense. Later we will get to know that this estimation error and this approximation error and this irreducible error further, right? So out there somewhere there is a magical predictor. So this is magical predictor h star, that is ideal, that classify everything perfectly. So this is ideal, and that is in real scenario it is not achievable, right? So this predictor is unattainable, and all we hope to do is use the combination of our domain knowledge and data to approximate that. So that is okay. Okay, so I think you have got some idea about this estimation error, approximation error, and irreducible error. Okay, now we see that we have three sources of error, and the three source, let me define, is the irreducible error is that the noise. So this noise is coming from the data generation process, right? So this we cannot reduce the further, right? And this approximation error is the bias square. And how, so you see that this approximation error, right? What we are looking at here, that the approximation error, that you see you have two terms here, right? And it is measuring how far we are from this true hypothesis, right? And if you have some sense about the last that we see that here this is the sample distribution around the true parameter, something like that, right? And here what it is capturing, that if you see that this difference is somehow we are measuring something from this true parameter, right? So this approximation error is going to catch the bias, right? And not exactly bias, but the bias is square, right? And what we can interpret is that how well can models fit data on an average, right? And this estimation error, you see that this estimation error is somehow we are measuring from some best hypothesis in the class, and with some hypotheses that are within the class that are trained from some our data, right? From sampled data, right? And this is what captures the variance. So how much model would change if we change the data set sample, right? So here you see that we have H1, H2, and maybe H3, and all these H are from the different sample and from the same distribution, right? So maybe if we change this H1 to H2, then how much that model would change, right? So that is what is captured under this estimation error, or you can say how much model is going to vary if we change the data set. Changing the data set doesn't mean that we will bring some irrelevant data. It means that we will sample from the same distribution in different time, and then we will check that how much it is going to vary, right? So this circle is the class of hypothesis, right? And all the hypotheses in this class are the hypothesis that we have trained from the same by sampling the same distribution from different time, right? And this is what this estimation error captures, that we call the variance, and how much models would change if we change the data set sample, right? So we can go more formal in mathematical manner, and we can see that earlier we have seen this. Let me go through it. We have seen the true error, right? True, or the generalization error here, right? And we saw that it is not possible to calculate this generalization error. So what we did is we divided our sample to some n and m minus n, and we call that this will our test data that haven't seen by our model, or we can say that we have only trained with the n example, and we have kept this n minus n example test hour. So instead of testing on some unseen data that is not even possible, what we are doing is we are testing it on the from the same distribution that we have taken, right? So we can, but the point is that we can decompose this error to these three, right? That the irreducible error, the approximation error, and the estimation error, and same way we can say that noise, bias, and variance, right? So let me just go through it, and I'm not going to do the complete math. So you can look at the book, right? So I will just show you that what the expression looks like, right? So here is our true hypothesis, and this is the output observed, and this is the noise, right? And this noise is normally distributed with the mean 0 and the variance sigma squared, right? And this is the feature, this axis feature. So this is again the true hypothesis, right? So what we are going to do at the first step, we are going to draw some n label points. So we are going to take the samples from this distribution D, and we are going to call this sample as a set S, right? And what we are going to do is we are going to train our model on this set S, and after training our model, we are going to get the hypothesis that we are calling HSX, right? And what we are going to do, we are going to pick the test point. So we are going to sample this test point from this distribution, right? So we are going to sample this test point from this distribution. Now what we are interested in, that what we have learned and what we are going to test this learned. So what we are interested in, that what our hypotheses have learned, and for this, and we have picked the test point from our distribution, right? So we are interested in how far they are from each other, right? So we are going to measure this error, right? And what is this? So we are going to estimate this error, right? So we are going to find the expected value of this error, and this is the same error that we saw as a form of this estimation error, and approximation, and irreducible error. So this is what we are going to get. That would be unavoidable error, that is the irreducible error, the bias square, and the variance square, right? So this is what the sigma square, that you cannot reduce further this error, and this is the bias square, and this is the variance. Okay, I think so let me just describe you that what is how you can interpret this and this one. So this is the true hypothesis, right? True hypothesis, and this is again so here so you see that this is our average hypothesis, right? And this average hypothesis, how we are calculating, is the average prediction over this set S. So what we are doing is that we are sampling again and again, and we will have some HS1x, again HS2x, something like that for each sampled example, training example, right? And we are taking the average of this, and that is what we are calling H average x, right? And this is the true hypothesis that is not achievable, right? So you see that, so this is the true hypothesis, right? So we are looking at that how far this H average is from the true hypothesis, right? So you see that something true is involved, so that is going to be the bias term, right? So this is going to be the bias score. And you see that this is a hypothesis learned from our data, that training example that we sampled, and we learned some hypothesis, and this is the best possible, or you can say the average of the hypothesis within the class, right? So what we are measuring here is the variance, right? And this is again the noise. right? So this is how you can interpret it. So if you see that this is the term that we look at the space diagram, that here the hypothesis space diagram, right? So this is your true hypothesis, and this is your hypothesis that is based in the class. So this is what we are trying to measure, and here that we're trying to estimate, and here we have some based in hypothesis, and we have some h hat, and this is what we are trying to measure. Okay, so that is okay. Now we want to draw this error versus the model complexity, right? So here we have some model that is not too much complex, and here we have model that is maybe some complex model, right? So if we have simple model, then obviously that we will have high bias. So this purple one represents the bias, right? And this blue one represents the variance, right? Because if we have if we are underfit, then the variance would be higher, right? And so this is bias square, you can say, and this is the sigma square, right? So this is the noise, that this green one, the constant one, right? And this is the true error that you see in the pink color, true error. Okay, now here the same thing I have I explained you, that here it is the same thing. So let's read it out. Variance captures how much your classifier changes if you train on different training set, right? And the bias, what is inherent error that you obtain from your classifier even with infinite training data. This is due to your classifier being biased to a particular kind of solution. In other words, bias is inherent to your model, right? And noise is how big the data intrinsic noise, the error measured ambiguity due to your data distribution and feature representation. You can never beat this. This is an aspect of the data. So that is what I have explained you, that, right? And okay, so how we can fight or address the, maybe you can say, variance or maybe high variance. So how you can fight or you can address the high variance? So increase the amount of data, right? So if you increase the m, you will have the less variance, or what you can do is the regularization, right? So okay, so if we have some something like this, with this you see we have the low bias, right? Because all the data points are near to some true parameter, and you see that we have spread in your hypothesis, so we will have this high variance. And once we do the regularization, right, so what is going to happen, right? So we are going to penalize some parameter, and we will have some less variance, but at the same times we are going to lose some bias, right? So here we will have some more bias than earlier, right? Because we have some low bias here, and here we will have some low bias, but we have trade off for the low variance, right? So with the regularization you can address this variance, right? So and how you can fight this high bias problem, right? So you can fight this high bias problem by increasing your maybe with the bigger class, right? So what do I mean by bigger class, right? So you see that here we have the high bias, right? Because all this hypotheses are somehow away from the true hypothesis, right? So it will have high bias, but it has some low variance, right? So we can trade off here the variance, and we can achieve the low bias, right? By increasing the variance we can achieve this, we can reduce the bias. Okay, I think that is all from this chapter, bias and variance trade-off.